Okay, this is number 42 from the book. Actually kind of a big problem, and for that reason I chose to just kind of show you the work that we're going to use to draw the graph. We'll go through it briefly, but then we'll kind of use all this information we've been talking about to get a good graph of the function. So here's the function. Y equals x minus 3 over x minus 2. Okay, and they ask us to graph this function using a lot of stuff, actually. They say using asymptotes, extrema, and intercepts as aids. And you can check on your graphing calculator, of course. Okay, well, what do we know? Let's start with vertical asymptotes. Okay, the denominator of this function, it's a rational function. The denominator is only 0 when x is 2. So that could be a vertical asymptote. Now, it turns out x equals 2 is a vertical asymptote because we can check the limits. When x approaches 2 from the left, the function approaches infinity, so the graph will curve up towards that asymptote at x equals 2. And from the positive side, the limit is negative infinity. So there will be an asymptote at 2 when x is 2, a vertical asymptote, and the function will curve down from the right. Okay. Also, there's a horizontal asymptote, and again, for this, there's guidelines in the books for finding a horizontal asymptote. It's kind of the second one. When you have a rational function, it's easy. What we're really trying to figure out is what does this function approach when x approaches infinity or negative infinity. But there's some quick guidelines in the book for this. They say if you have a rational function and the degree is the same, which it is here, this is degree 1 in the numerator and degree 1 in the denominator. Right, the largest power of x is x to the first power, okay, in both. So if the degree is the same, you have a horizontal asymptote, and it's found by taking the leading coefficient of the numerator, which is 1, and dividing it by the leading coefficient of the denominator. So the horizontal asymptote will be y equals 1 over 1, or y equals 1. So that's a horizontal line, okay. Now remember, vertical asymptotes are x equals a number, horizontal, or y equals a number. Okay, so two asymptotes, one vertical, one horizontal. Okay, now actually what I'm going to go ahead and do is erase this and at the same time try to keep it in my head so I can start incorporating this stuff on the graph a little bit. Okay, so we had a vertical asymptote at 2. Okay, so 1, 2. So right here when x is 2, there's a vertical asymptote, and now I'm trying to remember what we found exactly. Okay, yeah, from the left it curved up, so the graph curves up towards the asymptote. On the right side it curved down towards the asymptote. The limit was negative infinity, so something like that. Okay. But then we also found that there's a horizontal asymptote at y equals 1. Okay, so that means that our function flattens out closer to this horizontal line at y equals 1. Okay, so I need to indicate that on the graph. So something like this. Okay, vertical asymptote with the right behavior on either side at 2, horizontal asymptote at 1. Okay, so far, based on just that information, this is what I would draw on the graph. Okay. Now they also asked us to use information about increasing and decreasing. Okay. Yeah, I think their exact words. Well, their exact words were extrema. So do we have any extrema here? Do we have any maximums or minimums? Well, look at what we found by looking at the second derivative, or sorry, the first derivative. Okay, we found that the function is increasing from negative infinity to 2, right? So from negative infinity until 2, the function is increasing, which mine appears to be. Anyway, it is flattening out here. I need to be careful, but it is steadily increasing. Okay, and then from 2 to infinity, it's increasing again. Okay, my graph seems to show that. Okay, so it's consistent with that information. Basically, since it's increasing on both sides of that one number, by the way, where did 2 come from? It comes from that's the only critical number of the derivative, which I found here. But since it's increasing on both sides of that critical number, there is no maximum or minimum. Okay, and I can see that. In fact, the only thing that happens when x is 2 is the asymptote. Okay, so no extrema on this one. Okay, but what about intercepts? Well, these are just points we like to find when we graph anything. You find the y-intercepts by letting x equal 0 and solve for y. When we do that, we get 3/2 for y. So that actually is something I can change a little bit on my graph. The intercept is 0 3/2. That's the y-intercept. So 3/2 is about right here. That means when I make it bend down to the left, it needs to hit that particular point. So still increasing, moving up towards positive infinity at that vertical asymptote. but I corrected it a little bit to have the right y-intercept. And to find an x-intercept, you let y be 0 and solve for x. Of course, if y is 0, the only thing that's going to make this fraction 0 is if x is 3. So right here at 3, and it looks like I was pretty close there, there's an x-intercept. Okay, so tie all this information together. That's a pretty accurate graph of this function. You can go into the calculator and graph it just the same way for a backup. Just type in x minus 3 divided by x minus 2. But you're not going to see any surprises. The graph you get is going to look almost identical to this. You know, it might look a little bit cleaner, but really all of the important features we can find just based on this analysis of the function.